work on best practices to create virtual control population organic studies. APT mentor is Bosman and our Merck mentors are Danley, Islam Unis, and Matthew Wilson. We'll take us through post presentation and regular care. The way of production, conducting pharmacokinetic studies in organic impairment studies will require healthy control groups. Relevant regulatory authorities indicate that healthy control groups should have similar characteristics with the organic impairment, characterizing exposure, further guide, dosing recommendations for organic impairment. There is growing interest in the feasibility of using pharmacokinetic-based virtual control groups. This is because the use of action control is expensive and time-consuming. A recent study has assessed the feasibility of using simulation, pharmacokinetic modeling and simulation to generate virtual control groups that can replace healthy control groups in late-stage pharmacokinetic studies in participants with organ impairment. The study was done by our Merck mentor studies, and they looked at 7 marketed needed drugs, which are highlighted here. And you can see from here, they created a virtual control group from healthy participants in these 7 drugs, with the exception of Previr, which had no groups. The main outcome of the study was the geometric mean ratio between the observed and simulated for the CMAX and the AUC. What we can take from here, from the study, is the geometric mean ratio multiplied between 0.8 and 1.25, with the exception of the discordance from Previr. As earlier stated, they had no healthy control groups in the Previr study, which further suggests that the use of OPK model from organ impaired study would predict poorly for the virtual control. The main conclusion from the study is OPK-based virtual control participants can be used in organ impaired study. However, knowledge gaps still exist in that there is no standard procedure for creating control population group using the 4PK models and the application of this virtual control group in the spectrum of drug development process. With that, our objectives are to establish design space for using 4PK model to create virtual health control groups for PK studies in participants with organ impairment. This should include the extent of the data and timing of utilizing this approach in the drug development spectrum. And our second objective is to establish the best practices for development of 4PK models to create virtual control groups to replace healthy volunteer control groups for PK studies in participants with organ impairment. We work on 2 Merck-approved antibiotics, relebactam and imipenem. Relebactam is a beta-lactamase inhibitor that is active against beta-lactamase and is given in a fixed dose combination with imipenem and cilastatin. Cilastatin has no antibiotic effect, but it acts to inhibit the renal dehydrogenase that kills the imipenem. Imipenem is a carbapenem beta-lactam antibacterial agent that covers many gram-negative, some gram-positives, and anaerobes. The two drugs are renally excreted majorly. The data we worked on was from a published study that looked at the 2 drugs in combination in an IV infusion, both the imipenem and relebactam. It was published by Babunde et al. In 2009. They looked at the pharmacokinetic analysis for imipenem relebactam in healthy volunteers and patients with bacterial infections. The study comprised of 10 different studies, as you can see here, and they had different study design that ranged from phase 1, phase 2, and a phase 3 study. In all the 10 studies, only 35 had renal impaired participants, in which 30 had renal impaired and 18 healthy margin control participants. And in most instances, the impairment was on a fixed dose combination, whereas the relevant have varying dosing given to the participants. So our main aim with these different studies is for us to create 5 different scenarios that would be the studies here in combination or alone, with the exclusion of study 5 that has the renal impairment. The study 5 will be our reference study, in that our main aim is to see if we can have virtual PK model that might have similar characteristics with this 18 healthy matching control. The 5 different scenarios are: scenario 1 would be a single study, that is study 1, that will include a multiple ascending and single ascending study. For scenario 2, we would combine all the phase 1 data that was highlighted earlier. In phase 3, in addition to the first scenario, we will be adding proof of concept studies, the 2 phase 2 studies that we have. And then in the following scenario, we would add more phase 1 data to scenario 1 and scenario 3. And finally, in the 5th scenario, we would include the phase 3.
Connection dropped.
Yeah.
Keep going.
Apologies for the connection. Just a brief recap on the scenarios. The scenario 1 was study 1. For scenario 2, we had all the phase 1 data. For scenario 3, we had scenario 1 and we added the proof of concept studies, the 2 phase 2 studies that was earlier shown. For the 4th scenario, we added the scenario 1, 2, and 3. And for the 5th scenario, we added the phase 3 data. So in all these scenarios, we have to create virtual PK models and to see which one of these 3 best scenarios would mimic the virtual health control for study 5 that we earlier showed. This slide shows important demographic characteristics of the participants, and I'll take a little bit of time to explain the characteristics. So in study 5, there were only 48 participants, 30 having renal impaired and 18 are healthy control. For scenario 1, we only had 1 study with 83 participants. For scenario 3, comprised all the phase 1 studies, making a total of 184 participants. For scenario 3, we added the 2 phase 2 studies to scenario 1, which comprised 730 participants. And for the scenario 4, we had scenario 1, 2, and the remaining phase 1 studies. For the final scenario, we added a phase 3 data. So the important demographic characteristics in the participants were age, body weight, creatinine clearance, gender, race. These are the demographic characteristics, and the renal impairment was categorized into 4 different stages. With the stage 1, a creatinine clearance of more than 90 ml per minute, that means having a normal renal function. Stage 2, a participant having a creatinine clearance of between 30 to 60. Stage 3, having between 30 to 60 ml per minute, and then the last stage, severe renal impairment, a creatinine clearance of less than 30 ml per minute. What we can see here that in all these studies that have the healthy participants, some do have mild renal impairment. As we go further, we could see that the stage 5 also had the 18 healthy participants, and then here we have those that have severe renal impairment in this group. So for the gender, the first scenario was predominantly male participants, and overall there is preponderance of male participants compared to the female participants. And in the ethnicity, there were more people of white ethnicity as compared to other races. So the phase 3 data also had participants that have complicated urinary tract infection or complicated intra-abdominal infection. In the POP-PK building process, we developed 5 POP-PK models, and we validated each POP-PK per scenario. We developed a structural model for each of the scenarios, and we tested relevant covariates for the scenario. Models were validated by goodness of fit plots and individual predictive checks. So my colleague here will proceed with many parts of the presentation.
Okay. Thank you, Ali, for the presentation. Straight from where I stopped, looking at our aims, the aim of the study, trying to eliminate recruiting a healthy participant in organ impairment PK studies. So with the data we had and how it was partitioned, we did for each drug 5 models, each model a scenario. And from the final models, we did simulations. Then the simulations were done with, with 2 data sets. One was the data we had from Voter Profile that was not part of the study. And also we generated a second data set pulling features from enhanced database. For both 2 data sets, we used study 5 study design, looking at the adults and also healthy participants, considering the rating PRs. Then we conducted NCA, looking at the exposure between observed from the study 5 data and the simulated data from each scenario. And we considered AUC and CMAX as our main exposure parameters to generate the GMR or the geometric mean ratio. So first we looked at the GMR between observed and simulated from each scenario. And also we went ahead to look at the GMR between the renal category data versus controlled versus healthy participant or and simulated, of which simulated data here is assumed to be healthy participants because it was generated using the healthy participant final PK models. So we categorized the our renal impairment stages according to the criteria TRS as stated earlier into mild, moderate, and severe. So looking at the results from the PK models, Rebectam compartment, 3-compartment model described the data, sorry, 3-compartment model describe the data better compared to the rest of the compartment, and the covariates included were body weight, creatinine clearance, race on clearance, and for MEPNM, the 2-compartment model described the data better, with the body weight and creatinine clearance as our covariates. Then looking at simulation results for Rebectam case, we have 2 cases looking at the data we have at hand and the data would be used in case that study was not conducted, which is the enhanced data set. So we look at how the simulations from the 5 scenarios predicted the outcome. And we used the range of 0.5 to 1.25 as it was stated in our reference study. Then we compare the exposure using the AUC and the CMAX, of which they all fit within the range, supporting the study, our reference study that the virtual control populations can be used to replace the healthy participant in the PK study of organ impairment participants. So then when you look at those adjustments, so we first looked at the observed healthy versus observed brain environment from the protocol 5 study. And here the only parameter considered was AUC. So we looked at the ranges. In case we have mild, moderate, and severe renal impairment, what would be the differences in the exposure? So we categorize them and put them into their respective ratios. With GMR 1.5, 2.6, and about 4 for mild, moderate, and severe, respectively. So informing how those adjustments are needed with participants of in renal impairment category. So with that, then we carried it forward to look at how this one affects our predictions using our submitted data from 5 models per drug. So when you look at observed data in the brain and simulated data in each scenario, you can see that scenario 5 and 3, they predict the outcome better, with scenario 3 having sudden match phase 1 study data. Then with scenario 4, you can see there's a shift, and the shift is due to the addition of other phase 1 studies, because that was the scenario 3. Then scenario 5, that's addition of phase 3 data. So with the results from our 1 case study, it also supports that that simulated data can be used to replace the healthy participants in the renal impairment studies or any organ impairment study. And for our case, the virtual control groups can also be used to inform those adjustments. But for more cases are needed to strengthen our findings, as we are going to carry on with case studies from like more than 4 drugs. So I acknowledge our mentors for taking us through this journey, the Cetera Pharmacometrics Africa, and also Merck for this opportunity. Thank you very much. Any suggestion from Ms. Welcome?
Thank you. Thanks, Ronald. Thanks, Avi. It's a great presentation. So before I open the floor to questions, I see we were joined by one of our sponsors, Islam from Merck. And I believe Ronald, also one of the mentors from Cetera, is also online. So any comments and introduction from your side, please unmute or come and introduce yourselves.
Can you hear me?
Thanks, Richard. Yeah, thank you.
Yeah, sorry, I the voices keeps cutting, so I'm assuming based on the chat you're asking me to introduce myself.
Yes, thanks.
Okay, that's good. Yeah, so this is Islam Yunus. I lead the cardiometabolic group within the Department of Quantitative Pharmacology and Pharmacometrics at Merck. And I had the pleasure to, in addition to that, as the direct mentor to work with both Ali and Ronald on this project. This has been an exciting experience for us, and looking forward to repeat it in the future.
Thank you. Thanks, Islam. Okay, so online, if there's any further questions from this side. I'm not seeing anything on the chat at the moment. In-house, do you have any questions? Yes, breakfast, yeah.
Yeah, thanks for again an interesting presentation. I had a question on the GMRs and specifically the comparison of predicted versus observed. And I noticed the pattern where I'm wondering where does it come from? Seems in, I think it's the first comparison with the 5 scenarios. You look at Cmax and then you see you compare them predicted versus observed. You see a bit of a dichotomous profile for the AUC, which where you have an under prediction or an over prediction with the first 3 scenarios, I think, or at least there are 2 scenarios, one end on the left hand and 3 on the right, if I recall correctly. I was somewhat surprised that that happened for AUC. I would expect something like that to happen earlier for Cmax, given that that may be more dependent on the type of data that you have underlying your model. If you have rich data to support your model, it's easier to capture Cmax. If you have sparse sample data, then typically your Cmax is the first thing to be off your predictions. I was just wondering, because AUC typically is a fairly consistent metric that whatever data you have, you will get typically to the same AUC estimate because it's derived from periods. So just wondering, what may be the explanation there? Maybe I'm missing things. Could very well be the case. Maybe it's good to look at the plots.
Could you share your screen for the presentation?
Yeah, here.
Yeah.
Yeah, so you have the 3 blue on the right, no, right, and then 2 blue bottom on the left. The may actually be, I realize now, the NCA, we did a publication simulation and then an NCA estimation.
Yes.
Okay, so that may be. And I was happy to hear your thoughts there.
Okay. So it could also be due to the fact that when you move from scenario 2 to scenario 3, then you start bringing in participants with bacterial infection, where you expect the yes. So that one will alter the data so much, and the concentrations were high. So that's why you see the difference, the shifting.
So that has more impact on your AUC than it has on your Cmax. Okay.
Thanks for the presentation. That was very nice. I wanted to ask you 2 things. The first one is maybe a bit more methodological question. In the PK model, you say that you added body weight, right? And also GFR. How do you estimate the GFR?
The GFR was estimated using the Stroke-of-Goff formula,
Okay.
and included categorized the renal, the creatinine clearance into the 3 stages.
And did you watch, or did you take care of the duplicity of body weight discovery and also from the Krakow and Gold equation?
Oh, yeah.
Huh?
Well, what we first did was we did the allometric scaling for the weights. Yeah, but then we still proceeded to test the creatinine clearance based on the Goff formula as a covariates with that.
Okay, but so you have body weight as allometry,
Yeah.
but also
Yeah.
to estimate creatinine clearance.
Yeah.
I think that you need to be careful with that because then you are adding the effect of body weight twice. I mean, it depends. How do you estimate the clearance? Are you assuming the 100% of the clearance it is renally excreted, or did you estimate not renal and renal clearance?
Well, what the data that we got came along with is data specification key. That this is what was gotten. So the details on how they did that, we don't really have access to that.
Okay. Yeah, I think that is can be a recommendation. Just be careful because if you put it clearance plus allometry, it's not clear. The unit equation. So if you have clearance and on top of that allometry and on top of that Krakow and Gold estimates, you have body weight twice. But if you split it in renal and non-renal, and for the renal part, you only have, let's say, productive involved estimates, then you only have once the effect of body weight on that renal part. But if you put it as one single equation, you have that duplicity, and you are assuming that 100% of the clearance is really expected. And I don't know if there is close to reality or whatever the literature says. Okay, that's one. And the other one, I think that the biggest challenge for this is the extrapolation of the results, because you have, let's say, the races that you were including and the data that you have is not well balanced, let's say. And also, I think that you have as an effect, right? Can we see the covariates that you included? Race and clearance. What would be the reason why race can affect clearance?
It could be due to genetic differences, maybe also in a drug metabolism, because when you look at the data shown, there are some studies that were done independent in different populations. In Japanese populations, then independently, then in white populations.
Yeah.
Yes.
And would that be related to renal clearance or, let's say, hepatic clearance, or because then it will be different, right?
Yeah.
If it is, let's say, for cytochrome, cannot be renal, it might be hepatic. So that is why it might be important for you to split clearance into renal or renal, and maybe race can go to the hepatic part rather than the renal. That makes sense.
Yes.
Thanks.
Anyone else on the floor still has questions, comments?
Very nice work. Have you considered also simulating subjects with mild renal impairment? See if you can get the same results. And the reason I'm saying this, what you're doing here is a good extension foundation for avoiding healthy volunteers forward. But that's usually the easiest score to enroll. The more difficult ones to enroll are mild. So, have you considered doing that for this one?
No, the aim of this study is actually to eliminate the healthy volunteer from the renal impairment or organ impairment studies, because they don't have any benefit pertaining some studies. So what we are doing is simulating the only healthy volunteers, not renal impaired volunteers.
But this could be an extrapolation or an extension. If you use the very nice scenarios that you have in those public models and see if you simulate a cohort of 30 targets or wherever you have each of the targets of mild, moderate, and severe. If you can get severe, but maybe mild and moderate.
Yes, maybe using such ratios, you can extrapolate and also get the simulation.
That's a good suggestion, and if we are done with this, we'll consider
Project for next year, maybe.
2025. And that would be a good point to ask Islam to comment, actually.
Islam, do you want to comment on this? I'm not sure if you heard my question.
I'm having a hard time with the audio. Apologies. So can you write it in the chat? I'm not trying to be disruptive here.
Islam, can you hear me?
I can hear you now. Yeah, go ahead.
Okay, so I was suggesting, if this work can be extended to simulate subjects with mild renal impairment and moderate renal impairment and see if you will get similar results. I think you have done something similar to this, maybe in the past, but maybe you can comment on this more.
Yeah, I think it's a good idea. We have done this before, actually, when I was at the FDA. Mariam, we have 16 compounds where we have shown that we get good concordance when we try to simulate participants with renal impairment. The only thing that would not result in good concordance was when we have collinearity in the model. But yeah, definitely. I mean, at this point, we're focused on the control group, but definitely something that we're thinking about as we expand it. So yeah, it's a good suggestion. Thank you.